Okay, thanks very much, Karen, for the introduction. And thank you for inviting me to give a talk here this evening. Good evening, ladies and gentlemen. It's quite appropriate, given it's the 20th anniversary, because the very first platform, I think, was shared by Professor Peter Blood, who many of you will know in the audience here, and someone from Epitaxial Products International at the time called Steve Bland. And they talked about interaction between industry and university, and after 20 years, it's really come to fruition. So Nick showed me a photograph just before we started of me and Geraint at an event, and I've got jet black hair, black beard. So this is what interaction with the university does for 20 years. But anyway, so the title of the talk is about semiconductors, and we're going to focus on compound semiconductors. So semiconductors have really changed the world we live in. They've had a profound effect on all areas of our lives. They have changed the way we live, the way we work, the way we play, the way we communicate. I mean, it's hard to believe that in just a generation, you couldn't imagine that you'd have a device that you could sit in the palm of your hand and you could communicate with anybody on the planet, anytime, almost anywhere. Not in the Villa Glamorgan, unfortunately, but just about everywhere else. Semiconductors have been the engine of economic growth in all major societies over the last 40 years. They're fundamental to every major industry around the world, and they will be even more so as we go through the future. So just to give a little illustration, in 1969, with the best technology that NASA, which is the most powerful technology company on the planet, with the most powerful communications technology, Neil Armstrong was able to send 6 photographs back to Earth, and it took about half a day. Last weekend, 2 Cardiff University students, Tracy and Sharon, went to our party and in half an hour tweeted 153 high-definition photographs. So that's the power of what semiconductor technology has done over the past few years. And this has all been made possible by communications technology. So in 1996, when Cardiff Innovation Network was first launched, there were 35 million users. Today, there's about 2.8 billion internet users, almost half the world's population. And the same is true of handsets. 1996, there was 80 million handsets or handset users. Today, there's 3.7 billion handset users. So pretty profound changes in just that 20 years of the innovation network. This diagram is something which shows productivity on the left-hand axis here against time. And many of you would have heard of Moore's Law. Gordon Moore was one of the founders of Intel in 1960-something. And he predicted that over the next few years that the number of transistors on a chip would double every 18 months. And it became known as Moore's Law, and this is designated here in the green dots. But you may ask yourself, how did Gordon Moore just wake up one morning and suddenly think, oh, I think the number of chips on number of transistors on a chip will just double? Well, actually, he was very smart. What he did was basically just predict that the silicon industry would take over where discrete transistors had gone before and valves had gone before that and electromechanical devices. And so if you look at this productivity measured in calculations per second per $1,000, you can see on a semi-log plot it's a straight line. And this is what human beings do. We just innovate. We just make things better, faster, cheaper all of the time. And so Gordon Moore was a very clever guy in recognizing that this would continue through the silicon age. And now, with miniaturization, silicon's almost come to the end of being able to do that. We're down to 10 nanometer node. 10 nanometers is a tiny, tiny, tiny distance. And so other semiconductors are now beginning to come to the rescue. And the most powerful of these is a family of materials called compound semiconductors, which I'll talk about today. So just to give you an illustration of how powerful that dynamic is, 6 orders of magnitude change in productivity just over the cycle of Moore's Law. In 1978, a commercial flight between London and New York cost $900 and took about 7 hours. Not much different today, actually. But if the airline industry had changed at exactly the same pace and obeyed Moore's Law, then that same flight would cost about a penny and take less than a second. So that's the profound impact that semiconductors have had. Now, tonight we're talking about technology. The Oxford Dictionary definition is the application of scientific knowledge for practical purposes, and we're talking about innovation. And innovations is extracting value, making things of value from ideas. So let's look at compound semiconductors, and it's kind of appropriate that we're talking about the unsung heroes in a land of song and singing. So I think in the future we should, hopefully after tonight, sing the praises of compound semiconductors rather than be the unsung heroes of the world. So one of the key things that compound semiconductors contribute to is hardware. And of course we hear lots and lots and lots about software today, but without hardware, software just wouldn't work. And the two have to marry each other absolutely, hand in hand. So software, the silicon industry has been the great generator of the ability to calculate things faster and faster and faster with more and more chips on a computer. Whereas the hardware is brought about by compound semiconductors in general. So it allows all of that software to communicate and to make things work to the benefit of society. And just taking a few examples, here's some hardware, lighting. The lighting industry will be profoundly changed over the next few years by LED lighting. Every LED is made from compound semiconductors, mainly a material called gallium nitride. But not only will it save huge amounts of energy, so typically an LED light bulb will save about 80% of the electrical energy of an incandescent light bulb. And I notice the university is beginning to put LED lights throughout the place. But we can now create, using LED lights, exactly the same spectrum as sunlight outside. And it's the first artificial lighting that has been capable of doing that. And this is pretty important because light governs the way we feel. It governs, so if you're out on a sunny day, you feel a lot better than if you're out on a cloudy, rainy day. If you go to hospital, okay, there's a famous saying that if you have a bed nearest the window, you get out much quicker than somebody who's got a bed in an indoor thing. And that's because light, we've been controlled by light for millions and millions and millions of years. So it determines our hormones, our hormone production, how we feel, how health is governed. All of these things are governed by light. And for the first time, we've got an artificial light source which can change the spectrum of the light during the day in exactly the same way as the sunlight changes. So in the morning, there's a high element of blue light, which wakes you up. In the evening, there's a high element of red light in the spectrum, which makes you feel drowsy and goes to sleep. So if you sit in front of your computer late at night, a lot of people have difficulty getting to sleep. So there's an app out now which takes all the blue element out of a computer screen to allow you to sleep at night and still work late. So that's just one example, lighting. Another example is energy. So one of the most efficient means of generating electricity now is compound semiconductor solar cells, solar panels. Every satellite in space today is made from compound semiconductors because they're so efficient at converting sunlight into electricity. The most recent results are something like 47% of the energy in the sunlight can be converted directly to electrical energy. Equally, compound semiconductors are used to switch electricity. And it's a little known fact, but around the world today, the amount of energy lost through just switching electricity from one voltage to another voltage, like for instance in the socket coming out of the wall, there's 240 volts AC, your computer takes 9 volts DC. That switching, the little black box, the converter, if you touch it, it gets quite hot. And that's because it's incredibly inefficient. If you use compound semiconductors, you can reduce that efficiency, you can increase that efficiency and make it much more effective. And so if you look at the energy saving side of the equation, there's actually more energy lost in the world today through just power switching than all of the renewable energy generated put together. So whereas most governments focus on clean energy generation, they should really be focusing a lot of their energy on better use of energy. And compound semiconductors has got a very powerful role to play there. Got important roles in the aerospace industry, very important roles in the healthcare industry. So for instance, I don't know if anybody's got an iWatch here, but an iWatch today, you can strap it on, it'll tell you what your heart rate is, it'll give you some fitness data. But in the next few years, there'll be little lasers in there which will be able to penetrate your blood, and sensors which will be able to detect all the impurities there. So blood sugar levels for diabetics, for example, alcohol levels if you're an alcoholic, or you just want to know whether you're safe to drive home or not. But many, many different applications of sensors in the healthcare industry. Robotics, again, all the sensing in robotics will use compound semiconductors. And the automotive industry, you've all heard of autonomous vehicles. Well, all the sensing around and all that technology will feature a very large part of compound semiconductors. But perhaps the most important area where compound semis have impacted have been in communications. And if we just look at the history of communications, it really is the history of compound semiconductors over the past 20 years. So if we had 2K high-definition movies in 1988 when IQE was first founded, it would have taken 102 days to download that video. By the time 2G came along in 1996, it was a quarter of that time, 46 days. And then by 2001, 2.5G, only 6 days. So it was almost manageable. You could start downloading a movie on a Sunday in anticipation of watching it on a Friday night. Imagine that. When 3G came along in 2008, only 2.5 days, 3G Edge, 8 hours, 4G, 1.5 hours, and now today, it only takes 8 minutes using 4G LTE Advanced, if you can get it. Okay, so you're at the point where if you don't like a movie, no big deal. You watch the first 10 minutes, go make a cup of tea, and you can go and watch another movie if you want. But imagine when we get 5G, it's only going to take 4 seconds to download that same movie. But the problem is the technology in other areas moves ahead just as fast. And so we talked there about a 2K high-definition movie, but of course now we're getting 4K, and that means 8 times as much information. And then 8K means 64 times as much information. So all through the technology chain, we require more and more data. And of course, it's all about the chips. The chips are the things that make things work. And in a mobile phone, you've got lots of silicon chips, which do all the processing in the center of the phone, all the A to D conversion. But the key chips that allow the device to be not just a fancy gaming machine, but a real communication device are the communication chips. And these are the chips that allow communication with a Wi-Fi hotspot, with the satellite, with the base station, whatever it is. And you might wonder, what makes the chips work? Well, the simple answer is semiconductors, of course. Now, if any of you are chemists and remember the periodic table, here we are. Now, out of all these elements, there's a very small number of them which have some very special properties. And germanium is one of them, and silicon is one of them. And these are materials which have the ability to change their conductivity over a vast range, over many orders of magnitude, just by the introduction of some impurities into the crystal structure. So these were the two key semiconductor elements that first were discovered with those properties and have been used to make chips, germanium first and then silicon. Then obviously some bright sparks came along and said, well, what happens if we mix elements on either side of these semiconducting elements? Will they also be semiconductors? And so that's what they did. And lo and behold, people mixed up these various elements, and eureka, they actually ended up discovering that they had many, many different kinds of properties, from light-emitting properties to radio frequency properties, and very high-speed electrical properties. So just to go and give you a little bit of history on what happened since semiconductors were discovered, Bardeen and Shockley, they first demonstrated transistors using germanium at Bell Labs in 1946. The focus then switched to silicon, and Intel released the 4040 microprocessor chip, and it just had 2,300 transistors on it at that time. And by 2014, by miniaturization, that had increased to 3 billion transistors on the same size chip. Just a phenomenal amount. Through Moore's law, through shrinking the size of the transistor, now 3 billion transistors on a single chip. And of course, during that 50 years, everything has been as a result of Moore's law and scaling. And during the last 20 years, which has been the time of the Cardiff Innovation Network, compound semiconductors have really come into their own. IQE was founded in 1988. I used to work for British Telecom. They were looking at this newfangled concept of fiber optic communications, and they needed some material to do it, so they played around with various elements here and discovered that indium phosphide was a great material for long wavelength fiber optic communications. So how do we make these compound semiconductors? Well, we start off with a substrate. We then, by a process called epitaxy, we lay various elements down together, and you can see we can create gallium arsenide or aluminium gallium arsenide or any combination of these elements that I showed earlier. And that means that you've got a semiconductor which is virtually a designer semiconductor. You can design any property really that you want from these various elements. And as we get to more complicated devices, then we have to use more and more of these epitaxial films. But just to give you some idea of scale, even if we have 300 of these atomically engineered films, the total thickness is still about 1 or 2 microns. And given that the human hair is about 100 microns thick, then this still amounts to a fraction, a tiny fraction of the thickness of a human hair. And this is what does all of the communications, fiber optic communications, wireless communications, and everything else. So it enables these things to be pulled through by British Telecom and wireless to be introduced into all your smartphones and give you that phenomenal communications power. So all of this means that we've been able to take these few atoms and then put them into real applications. So the software engineers are so happy because they can develop so many apps on a smartphone these days. So many young guys can just go out there, start a business, become mega rich in just a couple of years through apps. And it's great to see the software university becoming a reality in South Wales as well as part of Cardiff University. And so we'll be generating many more entrepreneurial apps engineers over the next few years as well, I should imagine. But of course, the applications are not just mobile phone apps, but they're apps in all sorts of areas. So this is an automotive illustration. You can see how many of the applications in an automotive in a new car are governed by compound semiconductors or semiconductors. A huge number of the different applications will go into the automotive industry in a similar way to a satellite. So communication satellite today has all these different areas of semiconductor, compound semiconductor technology. And the thing that keeps it up in space are the solar panels, as I mentioned before. Very high efficiency compound semiconductor solar panels. So let's take a look at how these end industries rely upon the semiconductor industry. And what we've illustrated here is at the heart, you have the semiconductor materials. You then need to make them into chips. The chips then get put into components, packaged devices and modules, subsystems, then eventually integrated into the overall systems. So you can see the value chains that you can build up from the reliance on semiconductors, compound semiconductors, right to these end user industries. And one of the things that we've been working on as part of this whole network, or part of the whole cluster in South Wales, is these supply chains, these networks between them. So if we look in Europe at what's happening in terms of semiconductors to support European industry, there are essentially 4 semiconductor clusters. You can see them in Germany, France, Belgium, and in Holland. And of course, the UK is very obvious by its lack of having any real semiconductor center. And one of the things we want to do is we want to try to replicate some of the benefits of having these clusters, which is these clusters have about 800 companies. They employ about 150,000 high-tech jobs. And the benefit of high-tech jobs is that traditionally, or typically, the wage is about double the national average wage. And for every high-tech job that's created, there's another 2 jobs created in the local economy. So one high-tech job is equivalent in effect to 4 times that number of jobs in the normal economy. So we want to try and replicate this and put the same thing here in Wales. This time we want to make it, rather than a silicon cluster, we want to make this cluster a compound semiconductor cluster. So that's been one of the big drives of the past few years, is to work very closely with the local community, with Cardiff University, with the Welsh Government, and with industry to make this a reality. So one of the things the EU recognised and has recognised over the past few years, many of you will be familiar with framework programs, but one of the things that the EU has recognised is that a lot of high-tech manufacturing has disappeared from Europe. And part of the problem for that has been a lot of money has been focused in the framework programs on early stage R&D at TRL levels 1, 2 and 3, and a little bit in 4 and 5. A fact I learned the other day, an astounding fact, is that Singapore as a nation has got as much chip manufacturing capacity as the whole of Europe. Now, isn't that a scary thought? Europe only manufactures now about 5% of the world's chips. So the EU have seen this as being a really, really critical point, and they want to start reshoring advanced manufacturing back into Europe. And so one of the things they recognized is that there's been a lot of money focused in these regions, in TRL, early stage TRLs up to TRL 4 or 5, but not enough in supporting higher TRL levels. So under Horizon 2020, there are a number of programs now which are pushing towards the production end of things. So there's a big program called EXCEL, which stands for Electronic Components and Systems European Leadership, which tackles TRL 6 and 7 and introduces pilot line concepts. And so we've been working across the entire chain to try and put this whole cluster in place. And to enable the cluster to operate efficiently, what we really need is to have something or a number of entities working together which will cover this entire chain. And of course the big prize at the end of it is large-scale global production. So doing this, we are aiming to create the world's first compound semiconductor cluster, really put Wales on the world map, center stage, and create the first cluster which goes from end to end in terms of TRL levels. So what we've achieved so far is IQE's worked very closely with Cardiff University. We've, as Karen said, created this joint venture, the Compound Semiconductor Centre. And as a result of this, we've also lobbied the UK government very intensively and managed to persuade them eventually to George Osborne to announce a catapult, a Compound Semiconductor Applications catapult with initial funding of £50 million. So that was a real bonus for the region. And really what this represents is the building of foundations of a cluster. And I'll go on a little bit. Diana will talk a lot more about the Compound Semiconductor Institute, TRL level 1 to 3, and also doing a bit of prototyping at higher TRL levels, working closely with both the Compound Semi Centre and Catapult, device processing and testing the 200mm, links with high frequency engineering department, and leveraging Sir Cymru, which you are the chair of the Compound Semi Institute. So she'll tell you a lot more about that. I think everybody knows now it's a key part of the Innovation Campus, which is being built in the centre of Cardiff, a fantastic investment. One of the new 4 research centres and at Maindee Road. So I won't say any more about the Institute because I think Professor Huffaker is going to cover that in a lot more detail. I'll say a little bit about the Compound Semi Centre. So this is a joint venture between IQE and Cardiff University to then take technology to the next level, a combination of wafers and devices. It'll focus specifically on TRL level 4 to 6. Core enabling technology. The investment's about 30 million, cover a whole breadth of applications and will be in open access. And the director of this is sitting at the back there, so if you want to ask him questions later on, when Meredith's the director of that. And then the catapult is, it's an applications catapult. So the scope of that is also TRL levels 4 to 6. The government have announced 50 million core funding, but alongside that will be another 50 million pounds worth of grant monies over the next 5 years, and then they're expecting industry to also contribute a third. So the overall investment in this area will be quite significant. So you can see there's well over £100 million worth of investment now being put into this compound semi-cluster in South Wales. So the catapult will look at applications for end users, device and module modelling, a little bit of prototyping on the modules, integrating photonics with electronics, and working with systems integrators. So if we look at the map I showed you a little bit earlier of the supply chains, you can see that these 4 elements really provide a very sound basis from which to build these supply chains in South Wales to all of the major industries that we have around. And we're very fortunate in Wales actually to have representatives of most of these industries in the form of really world-class industry and names you will all recognize: Airbus, GE Healthcare, Siemens, Sony, Ford, Renishaw, IQE, Microsemi, and Infineon there, who have got actually the UK's biggest chip plant located across there in Newport. So one of the things we want to do is we want to commercialize now and move things from just the R&D and prototyping to world-scale manufacturing. IQE already has a network of manufacturing around the world, so we've built up a very strong leadership in the manufacture of compound semiconductor wafers, high volume manufacturing for the last 25 years, multiple production platforms, and across multiple facilities. So we already have, from a wafer perspective, we have global reach. We now want to change that to, or add to that, and make sure that we have global reach across all of the different industries that these materials serve: wireless, photonics, infrared, power, solar, and CMOS. So the routes to commercialization from a European perspective are pretty straightforward. What we hope to do over the next few years is to gain more and more programs under Horizon 2020. This covers the TRL levels right from early stage R&D through to prototyping. Excel is the program I mentioned, which will take it to pilot production. And then there's a new instrument being introduced for certain industries within Europe called IPCEI. It stands for Important Projects of Common European Interest. And as I mentioned earlier, the European Union have recognized that if they want to get high-tech manufacturing back into Europe, then they have to help companies right up to manufacturing. Now, in the past, investment by regions and governments in manufacturing has been governed by something called state aid rules. I'm sure many of you would have come across state aid rules. It was actually conceived by European countries when the EU was first formed to prevent governments funding their own industries. So they said, let's have a level playing field. We'll introduce these state aid rules, which didn't allow regions to invest in their manufacturing companies. Unfortunately, what they didn't realize is that they've handcuffed themselves against the rest of the world. So Taiwan, China, Japan, the USA has no qualms about investing in their core technologies and having an industrial strategy. So what Europe have now said is that to help us re-establish high-tech manufacturing, we will designate some industries as being of significant enough strategic importance that we'll call them important projects of common European interest. And thankfully, semiconductors has been designated as that, or will be, we hope, by the summertime. And as part of that, we have the Compound Semiconductor cluster as one of the core strands. So the significance of that is that when you look at the TRL scale, research, innovation, and production, you can see where hopefully where everything fits together here. Cardiff University here in the earlier stage R&D and perhaps a bit of prototyping. The Compound Semi Center definitely in the prototyping, and then the catapult in this kind of area. The programs Horizon 2020, Excel here, and then IPSI really supporting what's happening in terms of moving to production. And that's got particular significance because yesterday, as I think most of you will know, Cardiff City region signed a landmark deal with the government where the government's going to invest over £1 billion in the region around Cardiff. And of course, as a result of the Compound Semi catapult that the Chancellor announced in March, what he basically said was, this is a down payment on the city deal. He wanted to see Compound Semis at the hub of the innovation district. So that's what will happen. And the great thing about it is that if compound semiconductors are approved as part of this European IPSI, Important Projects of Common European Interest, it means that a lot of the investment will be able to be made into manufacturing and R&D leading up to manufacturing without contravening state aid rules. So this will make the investment even more powerful than it otherwise would be. So just to round up what we've been trying to do here, and I think we've managed to be pretty successful in conjunction with Cardiff University, the Welsh Government and now the UK Government. We've been successful in putting together all the foundations to create the world's first compound semiconductor cluster. And the next stage is building these supply chains out to the major industries around and create real wealth generation in the region. In fact, Cardiff University did an economic impact study towards the beginning of this project, and what they were able to show was that if we're able to achieve the goals of building out these supply chains, then the region would create about 5,000 new jobs, new high-tech jobs, equivalent to maybe 20,000 in the normal economy, and create between 25 and 50 new companies. So that's what we're aiming for over the next few years. We've had fantastic support from Cardiff University. This has been a true collaboration. So the seeds that were sown 20 years ago by Peter Blood and Steve Bland have come to fruition. And let's hope it carries on that way. Thank you very much.